recording our screen. Let's share our screen. Okay. Welcome to another week. We are in week 4, week 5. Where are we? Let's see. Yeah, we're in chapter 4, so that's week 4 of class. Force and Newton's laws. I know that last chapter, chapter 3, was a real pain in the neck, so if any of you have any other questions about that homework, feel free to send me an email tonight or tomorrow at the latest. Don't put it off, and we can help you work out the last few things that you might have on that one. Two-dimensional kinematics is a bear. And today we're going to enter the world of Newton's laws. So let's go to our textbook and let's learn all about Sir Isaac Newton. I actually learned something very interesting about Isaac Newton this past year, and that is that I have a relative whose name is Philip Packer. There's a great picture of him online. There's Philip Packer. There is actually a father and a son.
Your projector's not on.
Oh, my projector is not on, is it? Sorry. There's his daughters. He had a whole bunch of daughters, and he had a son. Actually, the son had daughters, or something, I can't remember. But he lived at Groombridge Estate, which is a really cool place. I'll show you. This is our family castle in Kent, England. It has a moat and a bridge across the moat and everything. But this guy, Philip Packer, was one of the original founders of the Royal Society, which was the first scientific society in the world. The first group of people to get together to promote science and to trade ideas about science. And they were in London, England. And they funded all kinds of science projects. In fact, if you've ever read Around the World in 80 Days, he is supposedly Around the World in 80 Days, the fictional book. The main character supposedly sends his writings to the Royal Society, but excuse me. Anyway, the reason that this is connected to Isaac Newton is because right before Philip Packer died, Isaac Newton was inducted into the Royal Society. And so they probably crossed paths a few times there. My ancestor Philip Packer was an architect, and he designed this castle, Groombridge Place, here, among other things, in England. Some bridges and other things, but anyway. That was back when, of course, that was like in the 1500s. So that was back in the day when they were still figuring things out when it comes to building things, figuring out what worked and what didn't. Kind of cool. But anyway, let's get into it. Newton's laws. Whenever I see dolphins, I always think of The Hitchhiker's Guide to the Galaxy. Anyway, great book. A great book and a great movie. You should watch it. Anyway, Isaac Newton's book, Philosophiae Naturalis Principia Mathematica, which means the principles and philosophies of physics and the mathematics of physics. And it was really the first physics textbook ever written. and maybe even the first math book ever written. Because in this math book, he also introduces the idea of calculus, which was necessary for him to do his work. He needed to invent calculus at the time. This is something that all great physicists end up doing at some point. They end up going so far beyond what anybody else is doing that they have to invent their own mathematics to get to the next level. Einstein had to do it, and let's see who else had to do that. Newton, of course, had to do it. Several Greek philosophers and scientists had to do that, including Galileo and others. But it was Isaac Newton who came and put it in a book for the first time. And he wrote his book, he published his book in 1687. It's rumored that the book was written maybe as many as 10 or 20 years before that. But Isaac Newton was notoriously secretive. He had a lot of weird beliefs. He believed in the occult, and he believed in witchcraft and other things, but a lot of people did at that time. You have to understand that that was not uncommon at the time. But he was trying to overcome a lot of those things. He was trying to prove some of them right and some of them wrong and other things. But what we're going to talk about with Newton today, and Newton's philosophy of science and math is not just about what we're going to talk about in this class. It covered things from like heat and atoms and electricity and light and all kinds of things. And many of the things that he wrote about, he got right, and many of them he wrote about, he got wrong. They were eventually proven wrong. But we're going to talk about, in particular, 3 particular laws that he observed. So does anybody know what the first law of Newton is? Newton's first law. Objects in motion tend to stay in motion. Okay, that's one way to say it. I would say that that is true, but maybe not quite as complete as it could be. Okay, you could also say objects at rest tend to stay at rest. Unless acted upon by an outside force. Okay.
I've heard it 2 ways. I've heard it where objects in motion tend to stay in motion, and objects at rest tend to stay at rest. It's the first law, and the second law is unless acted upon. And then I've also heard it where the first one is objects in motion tend to stay in motion unless acted upon, and objects at rest is the other side. So I don't know.
Yeah, there are a lot of ways that people talk about Newton's first law. But what it really comes down to is that things that are moving along in what we call an inertial reference frame, and that inertial reference frame means that it's moving along at a constant speed, in a constant direction, so it has a constant velocity, tend to keep doing that. And since zero velocity is considered a velocity, then that is also true in that. But the real deal here is that mass is the thing that causes this. And that's actually kind of a mystery. We're not exactly sure why mass does this. We're not sure why mass resists change. Why mass doesn't like to do something differently unless it's forced to do it differently. We don't really know why. There are a lot of theories. There are some models about that, but it's one of the big mysteries. And that's why Newton's first law is a law, because it's not something that can be proven. It's only something that we've observed. It's not something that can be mathematically determined or proven with any kind of experiment. It's just always been observed that way, and it's never been observed differently. So it's a law. We're going to be studying this idea of things having mass, doing what they do, and then forces changing what they do. And this study is called the study of dynamics. So dynamics, in short, is the study of objects, moving objects, objects at rest, whatever else, and the forces that can affect them. So what is a force? Anybody have a good definition for a force? An action.
An act upon something.
Okay. Force can act upon something.
The best I got.
It's actually simpler than that. An action, I think, is a little too broad because it's gonna bring in a lot of things that maybe aren't forces, but it's a good thought for sure. Anybody else? Simpler? Yeah, a push or a pull, right? And we're actually in section 4.1 of the book here, developing this force concept. Here we have this picture of these skaters. And why do we make skaters? Because skaters are on skates, which are metal blades on the ice. The metal blades tend to melt the ice just a little bit and create this little barrier of water between the blade and the ice. And that little barrier of water creates this really low friction sliding capability between the blade and the ice. And that's great because then you can slide along the ice, you can push off, and you can slide and slide and slide. Very little friction. And we're going to assume very little friction in many of the things that we do in this chapter. In the next chapter, we're going to assume all kinds of friction. But in this one, we're going to assume very little friction. So we have these skaters that are on the ice, and they're going to push this skater in the blue suit here. And this skater on the left is going to apply a force, a push, to the right. We're going to label that with a vector. Force 1, it has a direction, it has a magnitude. Of course, the length of the vector tells you how much force there is, and the direction of the arrow tells you which direction it's in. And then this skater behind the blue skater is going to push forward with force 2, or push upward, or however you want to think about this. So we have force 1 and force 2, and the combined force, since these are vectors, will add just like velocity vectors or displacement vectors, put them head to tail, and you get this third vector, which is the sum of those two vectors, the total force. Now, if you were doing this experiment, I think it would make sense. You know, one person pushes from the side, one person pushes from the back, and the person that's being pushed goes to the side and forward, right? And that kind of makes sense to us. So, but it's a vector concept, and so we can treat it like a vector just like we've treated other vectors in this way. This drawing or this situation can be represented in a much simpler form, which we use a lot in physics, called the free body diagram, where we represent the skater as a point. We do that a lot in physics, where we represent something as a point. We just assume that it doesn't have any shape or size or anything, which is not a great assumption sometimes, but it's a decent assumption sometimes. So we start off with it to make things simple. Then we represent the two forces going away from that point. Sometimes people draw free body diagrams with forces pointing at that point, but most of the time we like them to point away from the point. That is the point of interest. So the point represents the mass of interest that is having the force applied to it, and then you have these arrows representing the forces being applied to it. And this is a free body diagram. Often, another thing you would include in a free body diagram is a little, maybe a little coordinate system, so you know which way is x, which way is y, which way is z, or whatever else. Which ways are positive, which ways are negative, your origin. You might include things like that as well. But a free body diagram is called a free body diagram because it is considered to be, the point is considered to be the body that is free to move, and then you have these forces that are going to maybe make it move. So here's another example of a force. You have a mass on a spring, right? And you have a handle on the other end of the spring. And you pull on the handle and it stretches the spring, which eventually will pull on the mass that's at the end of the spring, right? But what do you know about pulling on springs? Have any of you ever pulled on a spring or pushed on a spring before? what happens? Is there another force involved? Is it just you pulling on the spring?
No, there's a tension.
There's some tension in the spring. What did you say, Packer?
I said there's a secondary force. I believe it's called coercion. No?
Torsion.
Yeah.
In a coiled spring like this, it is technically torsion. But I'm thinking the force that you feel. Do you feel a force as you're pulling on the spring? That force that you call torsion. Cassidy's nodding yes. What is the force that you feel when you pull on a spring, Cassidy? Which direction is it, for example? If you're
pulling it back, you feel tension in your arm, and like it feels like if you let go of all that in, and it's just gonna snap back.
That's right. So it's actually, if you're pulling it back towards you, which way is it pulling you? Away from you, right? Towards it. It's an opposing force, right? And like Packer said, it does have something to do with torsion. It has something to do with, and like Cole said, it has something to do with tension. And it is an opposing force. We don't really care about where it's coming from at the moment. We'll learn about that later. But there is an opposing force in here. So you have the pulling force of the person, you have the pulling force of the spring. Those two forces are in opposite directions. And that happens a lot in physics, where you have forces that crop up because of something you're doing. And we're actually going to learn a little bit more about that with Newton's third law. So, in this book, they call that opposing force a restoring force. In other words, this spring has a position that it stays in when it's relaxed, and when you try to stretch it, the restoring force tries to restore the spring to its original condition or its original position. And you can use that, to your advantage inside of what we call a spring scale. If you have a spring scale that is set up so that you know how far the spring is going to stretch depending on how much force you apply, you can use this spring scale as a measurement for force. We will use that this week in our lab. So, Newton's first law of motion, law of motion, not law of emotion, law of motion, is called the law of inertia. And inertia is a word from Latin, I believe, and it means to remain, or to stay, or to be unchanged. And this is the book's version of Newton's first law of motion. A body at rest remains at rest, or if in motion, remains in motion at a constant velocity, so that's a constant speed and a constant direction, unless acted on by a net external force. And we touched on all those things in our different definitions, which is just fine. And what does this mean, a net external force? We talked about an external force, but what does net mean?
It has to at least equal other forces. It can't, if you have two forces of equal power in direct opposition to one another, it won't do it.
Okay, so that's a good way to explain it.
It's accounting for all forces.
It's accounting for all of the external forces on the object that are acting on the object. So if you have more than one force acting on the object, you have to add those forces together to create the overall force. It's very similar to what we did in the last section with the ice skaters, right? We have two forces acting on here, force 1 and force 2. The net force is the sum of the two. It's just as possible to have one person pushing from the left and another one pushing from the right over here so that they're opposing each other, but one of them pushes harder. And you could still have a net force if the person on the left was pushing harder to the right than the other person pushing to the left, then you would have an overall net force to the right. But you still have to add them together to understand if there is any net force on this particular object. So it's the net force that really matters. And it does have to do, it is directly related to mass. So an object that has more mass has more inertia. In fact, when you get into Einstein's theories, they refer to the mass of something when it is sitting still, the inertial mass of something. Because inertial mass is different than moving mass. It turns out that as you move faster and faster and faster, you actually have a strange phenomenon that occurs which is that your momentum increases. And it doesn't increase linearly with the linear increase in speed. So it actually increases more quickly. And so there's something that's strange about inertia as you get going very, very fast, closer to the speed of light. I'm not sure what that is either, but it's very interesting. Excuse me. Okay, so now we've got an idea for what force kind of is, and we know kind of what mass and inertia are, Newton's first law of motion. But now we get into Newton's second law of motion, which comes down to Newton doing a lot of experiments. And as he was doing these experiments, he took a lot of data, and then he graphed out the data, and he got a line which gave him a slope. And the slope gave him an answer. And what is that answer? Well, the answer is Newton's second law. He learned that the acceleration of an object of a particular mass was proportional to the force that acted on it. So if he added more force, twice as much force, he'd get twice as much acceleration for the same mass. And 4 times as much force, he'd get 4 times as much acceleration for the same mass. And in another analysis that he did, he discovered that the acceleration is inversely proportional to the mass. So that if he increased the mass by 2, he would decrease his acceleration by a factor of 1/2. And so on and so forth. And through this, he was able to determine that there is an equation that governs motion when it comes to forces. This is usually how this equation is shown. Force net equals the mass times the acceleration. Notice the bold print. The force is a vector, the acceleration is a vector, the mass is a scalar. So the mass scales the acceleration to equal the force. If you just want to know the magnitude of the force, you just want to know the overall value of the force, then you can go ahead and just multiply the mass times the acceleration, not worry about which direction it's pointing, and just say, hey, there was this much force. But if you actually want to know which direction that force was applied, then you should probably think about that from the very, very beginning and include that in your work. So if this is the equation for force equals mass times acceleration, what are the units of force? Well, mass is in kilograms, acceleration is in meters per second squared. So voila, you get kilograms meters per second squared is the unit for force. And in deference, in honor of Isaac Newton, we named that after Newton. So Newton gets his own unit in the physics world, the Newton, the unit of force, which makes perfect sense. He did a lot of work for force. Now, let's take a look at this in terms of something we've talked about a little bit before, which is gravity. We've talked about how gravity affects things that are flying through the air when it came to trajectories of projectiles. And we talked about what gravity does for somebody. We've done sliding down a hill. We've done, what else have we done? I can't remember. But anyway, we've worked a little bit with gravity. But when we start putting in Newton's second law, we actually get our own equation for the weight of a person. Remember that force is the mass times the acceleration, but what is our weight? Well, our weight is nothing more than our mass being accelerated by the Earth. And if we're weighing ourselves on the scale, I have a great green scale over here, it's green and fuzzy. Let's see if I lost weight today. I doubt it. Oh, that's not bad. I'll try on both scales, see if I measure on both scales the same. Nope. So if I split the difference between the scales, then I probably just kind of stayed the same. But what is that when you're stepping on a scale? That's a force. It's the force of your body being pulled towards the center of the earth, and the scale gets in the way, so your body pushes on the scale instead of the earth. And as your body squeezes that scale against the surface of the earth, or in this case the floor of the science center, then you're going to be engaging the device inside the scale. Now most of these scales actually just use a spring. They use a spring that turns a little dial, and you get your weight. Why is my internet connection unstable? I don't know. But we can write our own equation for this. Instead of force equals mass times acceleration, we know the acceleration that gravity pulls on our body with. It's the same as in the projectile motion part. It's the same as everything that we've done with gravity. It's g, 9.8 meters per second squared. So we can replace the a with g. Our mass is going to just be the mass of the thing that we're weighing. And then the force, instead of calling it force, we're going to call it weight. So we get weight equals mg instead of force equals ma. But it's the same equation, just specialized for this particular use. We have a 1 kilogram object that we want to find out the weight of in newtons, so we go ahead and use in grams, or sorry, not in grams, I'm looking at g thinking grams. For g is equal to 9.8 meters per second squared on the surface of the earth, and we're going to find the 1 kilogram object weight. And we just multiply the 1 kilogram mass times 9.8 meters per second squared to get the 1 kilogram object weight. It ends up being 9.8 newtons equals the weight of that object. Now 9.8 newtons is about 5 times the number for pounds. For about 10 newtons you get about 2.5 pounds. And this is the unit we're going to use for weight and for force in physics, but not many people like to use it when they're in the gym, because if I was going to the gym, I'd have to report my weight as 900 something. And most people would have to report their weight as in the high hundreds, close to 1,000. I think that if you're 100 pounds, you're still going to be over 500 newtons, or close to 500 newtons, a little under that. So it's not very flattering to use newtons for weight, but it is a measure of force, like pounds is. So what is the difference between mass and weight? Mass is measured in kilograms, weight is measured in newtons, which are kilograms meters per second squared, but really what's the difference between them? Does anybody know the difference between mass and weight?
Weight is specifically the amount of force applied to something in the downward direction like gravity.
Yeah, so weight is a force that gravity puts on masses, right? Gravity acts on mass and applies an attractive force to mass. So all gravity forces are attractive. You have two objects with two masses, they will attract each other. And weight is just a very specific version of that. When you're standing on a mass that has a huge amount of mass itself, it's going to attract your little mass towards it, and you're going to feel pressed down to the planet, or pressed down to whatever. So who has an idea for what mass, the definition of mass should be?
The amount of stuff in object.
Yeah, you could definitely say it's the amount of stuff that something has in it. If we think of it, I'm sorry?
No.
So, in terms of Newton's first law, we can actually define mass as this amount of stuff which is determined by its inertia. Because if you want to know if something has a lot of mass, throw it at somebody, right? If you throw something that has a lot of mass at somebody, then, like a lot of mass meaning, let's say that 100 kilograms is a lot of mass. If you throw 100 kilograms, and 100 kilograms is a lot of mass, if you throw something that's 100 kilograms at somebody, you're going to hurt them. And it doesn't matter if you're on Earth or if you're in space or on the moon or anywhere else. It doesn't matter what the gravity is around you. If you can pick something up that's 200 kilograms, which you probably can't, if you can pick it up and throw it at somebody, it's going to hurt them pretty much the same way on Earth, in space, on the moon, or whatever else, because it's the mass. The mass itself is the thing that, for some reason, carries that inertia and allows objects to keep doing what they want to do and to bowl anything over that gets in their way if something wants to stop them from keeping to do what they want to do. Oh, so let's get busy with an example. Whenever I see this lawnmower problem, which we always do in physics, I always think of this picture of this guy that I saw who was balding on his head, and he has a lawnmower tattoo on his head, on the edge of his hairline. It's hilarious. So here we have a guy that's going to be pushing on this lawnmower, and it says that he has a net external force. Now this force is acting forward on the lawnmower. It turns out that the force on a lawnmower's handle is actually going to have to transmit itself through the handle. So the force on a handle on a lawnmower is actually downward, like downward to the right in this picture. But they're not telling us just the force that he's applying to it. They're telling us the net force that's being applied to the lawnmower is forward. So in other words, the downward part of this force, something is counteracting it. Something is canceling it out. We'll learn more about what's canceling that out later. Actually, it's not even that hard to think about. Let's think about it. Let's do a thought experiment. So let's imagine that our force on this lawnmower is not this. We're not going to talk about the net force that pushes the lawnmower forward. We're going to talk about the actual force which pushes down the handle of the lawnmower. So it's right in line with the handle of the lawnmower, going downward to the right. Now, if you push downward on a lawnmower, are you going to make it go anywhere?
No.
We have a vote for no. Why not? What gets in your way if you try to push a lawnmower downward?
The handle will be nothing there, you have a lever.
The handle.
Well, I'm thinking of it as a lever with the back wheels and as its axis.
Oh,
So if you push it straight down, you're going to get.
I'm just talking about the whole lawnmower as a whole. If you try to push the lawnmower down, there is an object that is not the lawnmower that's going to get in the way and push back. What is that object? The earth, right? So if we try to push the lawnmower downward, the earth is going to push back, and it's going to push back hard. And it's not going to let us accelerate this lawnmower downward. No matter what he does, he's not going to mow into the ground to China. Right? There's too much stuff pushing back. And that stuff is the earth. Right? So there's kind of this opposing force that the earth can give up at any time, and it can cancel out downward forces. So whatever downward force that this lawn mowing man is pushing downward on his lawnmower with, whatever force that is, that downward force is going to be counteracted by an upward force from the earth, and it's going to cancel out. So the lawnmower does not accelerate in the up and down position at all, in the up and down direction at all. However, it does have a net force forward. There might be a little bit of resistive force in the grass on the ground, but we're not talking about resistance. But this is the overall forward force on the lawnmower, represented by that vector now. It is 51 newtons to the right. They want to know at what rate does the lawnmower accelerate to the right? Well, we have an equation for that. Force equals mass times acceleration. It's the net force equals the mass times the acceleration. But we need to set this problem up a little bit more carefully. So let's go ahead and do it. the first thing I want to do is show you how to draw the free body diagram for this guy. So here is our lawnmower. Ooh, that's beautiful. And our lawn mowing man pushes downward on the handle, just like that. And one of the forces that is associated with that downward push is the forward push, which they're calling force net. That's the force net in the problem. Right? And the other one is the downward force. Now the downward force ends up being, we need to erase something really quick. I draw this too big. Oh, there's my eraser. Okay, so the downward force on this guy, we've got the forward force and we've got this downward to the right force, but then there's a third force that is downward like this for that net force. So it's like, well, sorry. Did I do that right? No, I didn't do that right. Okay, so we have a force, oh, I know what it is. We have a forward force, we have a downward force, there we go. But the force that he actually pushes with is this one. So this one is the push, downward and to the right. This one is just to the right, and that they ended up calling that our force net. Like that. And then we have this downward force. Can't draw. Downward force, okay. That's terrible. It's probably because I didn't get much sleep. There you go. So if you add that downward push to this other push, you do get a forward force in the end. Sorry, if you add the net force to the downward force, you do get the push that we push with here. But you can also represent this in a free body diagram, which you need to get used to using. So let's do a free body diagram really quick. So a free body diagram is represented on paper by what shape? The dot. We reduce everything to a dot. Okay, so this is the time that I tell a joke. This is a classic physics joke. Are you ready? So Packer's probably heard this one, I don't know, 100 times. But you have a physicist, an engineer, and a biologist, and they're all hired by a horse racing guru to help him win the next Kentucky Derby, right? And the biologist says, oh, we're going to do all the latest stuff with medicines, and we're going to give him steroids, and we're going to pump up his muscles, and we're going to do all this electro stuff to engage his muscles and all these things. We're going to have your horse going super fast, super chemical foods and all these things. And he says, that's great, get started. And then the engineer comes to him and says, we're going to use all kinds of biomechanics and biomedical research, and we're going to make prosthetics, and we're going to have a training regime that uses machines that are going to help this horse to run most ideal, this, that, and the other, and we're going to make this, we're going to help you win this race. And he says, perfect, get going on it. And then the physicist speaks up and he says, well, first of all, we're going to help you to win this race no matter what happens, no matter where it happens, no matter who's racing in it, we're going to guarantee you to win. He says, well, how are you going to do that? He says, well, first we have to assume that a horse is a point. It's not very practical to assume that things are a point. So when we get into the real world, we won't be able to assume things are a point anymore. But it does get us started. And even physicists and engineers that are working in the real world often to start with a point. So I've got this big ugly point here. I just decided I'd make it crazy big. So this is my lawnmower, and I want to know what are the forces involved here. Well, of course, I have this net force that is off to the right. Force net. Try and write that a little bit better. But we also have the actual force that the person is pushing with, which is the downward to the right force. So we'll call this the actual force F. And then we also, this forward force and the addition of a downward force is what gives us this overall force. So it gives us both a forward and a downward. So we'll call this F down and FD. Good to go. And it's often the case that when you're doing a problem, when physicists do a problem, is they draw a picture first of the situation in general, and then they draw a force diagram that's much simpler, just to map out the forces. Okay, so in this lawnmower problem, we know that, first of all, the lawnmower force is about 51 newtons. That's the net force that's exerted on the lawnmower. Notice that they said the net external force, the push minus the friction. So they've already done that math for you. And then they say it's parallel to the ground. The mass of the mower is 24 kilograms. So we know the mass, we know the force, and we can rearrange our equation. Force equals mass times acceleration will give you acceleration equals force over mass. Once we've rearranged it, we can calculate the acceleration in this case, the magnitude of the acceleration. We won't be able to tell you the direction of it yet, but the magnitude of the acceleration is 51 kilogram meters per second squared over 25 kilograms. So it equals 2.1 meters per second squared of acceleration of this lawnmower. So now we know the acceleration. What can we do with acceleration? Well, of course, we can use it in kinematic equations and drive ourselves nuts. But we're using Newton's second law now to calculate an acceleration of an object. Here's another example, the rocket car. Very cool, very cool. Says this rocket car was mounted on rails propelled by several rockets. We want to calculate the magnitude of the force exerted by each rocket, called thrust, for the 4 rocket propulsion systems shown in the figure. The sled's initial acceleration is 49 meters per second. So it starts out at 49 meters per second squared, and then it says the mass of the system is 2,100 kilograms. The force of friction opposing the motion is known to be 650 newtons. So we have all these forces up here in this opening paragraph. Let's make a picture of them. Here's our rocket sled. We know that there are thrust forces coming out of these rocket sleds, these rockets in the back of the sled, rather, that are going to push the sled forward. We know that there has to be a force back there that's pushing forward because the sled goes forward. And that's the gas that comes out, or the expulsion of the exhaust out here, is the thing that ends up giving this thing a push forward. But we have some other forces involved too. We have the friction that opposes that forward motion. And we also have the weight of the sled and the weight opposing force from the ground or from the tracks. That's what we were talking about a little while ago. We were talking about this opposing force that acts upward on the lawnmower when we push downward on the lawnmower. And this force we're going to have a name for now. We're going to call it the normal force. Normal does not mean it's regular. The normal part of the normal force means it's actually orthogonal or 90 degrees. That means that the normal force is going to act 90 degrees with an angle of 90 degrees with respect to the surface or the interface where this normal force takes place. So here's the surface, our tracks, and the normal force is perpendicular to that. If this was a circle, like a loop-de-loop, then we'd have to move that normal direction all over depending on where we're doing the problem. But in this particular case, the weight and the normal force do essentially cancel each other out in this case. as long as this thing doesn't start to fly. So, in this case, what do they want us to find? They want us to find the thrust force. Okay, so the net force is equal to mass times acceleration in Newton's second law, but also the net force is going to be equal to the sum of all the forces. In this case, we have a sum of 4 forces and a subtractive force in the friction. So since there are 4 engines, 4 rockets on this sled, then we have to take the thrust from one of those rockets, which is the force pushing the jet car forward. We have to multiply by 4 because there are 4 engines on there. Then we subtract off the only other force in the problem, which is the friction, which pushes us backwards on this thing. The friction is always in the opposite direction of motion. Always in the opposite direction of motion. Don't forget that. Friction is always in the opposite direction of motion. So, the equation becomes 4t minus f from that force. Now, if we put back in the mass times acceleration for the net force, down here in this equation, this is what we get. 4t equals mass times acceleration plus friction. Isn't that nice? Because now we have something we can solve for the thrust, or we can solve for the mass, or the acceleration, or whatever else. In this case, they want us to solve for the thrust. So the 4 times t has to equal the mass times acceleration plus the friction, and we just plug in the numbers here. 2100, 49, and 650. Can I read that? Yes, I can read that. So when we plug in those numbers and do all the arithmetic, we get 1 times 10 to the 5th newtons, which is reasonable. 1 times 10 to the 5th newtons is a very reasonable thrust for a small jet engine or small rocket engine. Each individual thrust, when you multiply that by 4, you get 2.6 times 10 to the 4 newtons, which is also reasonable. They are large numbers, but they're reasonable numbers for newtons, because remember that newtons are 5 times bigger than pounds. So if you take any one of these and divide by 5, if you take this one for example, divide by 5, 1 times 10 to the 5th, divide by 5, 10 to the 5th, remember, is hundreds of thousands, so that's 100,000. Divide that by 5, you're going to get 20,000. 20,000 pounds of thrust is a standard jet engine. Let's see. None of these that I want to go over really quick. Okay. So that's Newton's second law, the idea that force causes an acceleration, and that the force is directly proportional to acceleration, inversely proportional to the mass, and that there's this equation, force equals mass times acceleration. It's important for one thing, in many things in physics, to define what we call the system. Right here they're talking about the system. It is defined by the boundaries of an object or collection of objects being observed. All forces originating from outside the system are considered external forces, and that's why it's important, because we need to know what is an external force. An external force is something that is acting from the outside of your system of interest. The things that you're interested in seeing what happens to are your system, and sometimes physicists will draw a circle around that system, a dotted circle or a dotted box or something in their drawing just to make clear what they're talking about. Clear what they're calculating things about. I want to get to let's sign in here. I want to get to the homework really quick. Let's see. Okay. Let's see, 4.5, 4.4, 5, 6, 7, 8. Yeah, we'll do Newton's third law really quick and then we'll be done for a little bit. Okay, so moving on to Newton's third law. Where was I? Here we go. So what is Newton's third law? Newton's third law is kind of weird. Normally, when we have something that we experience a lot in our lives, we tend to understand it better in the classroom. But in the case of Newton's third law, that's not really true. This law tends to confuse the heck out of students every single year. And it's even confusing for teachers of physics from time to time, figuring out how this is working in the world around us. But it is certainly something we have a lot of experience with, but we take it for granted. Newton's third law of motion says whenever one body exerts a force on a second body, the first body experiences a force that is equal in magnitude and opposite in direction to the force that it exerts. Who can give me an example of Newton's third law in action? We've often heard of this law called opposite and equal reaction, action-reaction kind of thing, right? Who can give me an example of Newton's third law in effect in everyday life? Yes, Becky.
Drop something, if you drop it down the ball, it comes back up.
Okay, so what you're saying is that we exert a force with the ball on what?
Well, we allow so we lift it up, if you lift something up.
But we're talking about forces here. So the ball is going to exert a force on something. What is that something that's going to exert a force on? This is a good example for this. So what is it? The ground. This is a great example for this because it illustrates exactly what I'm talking about. The ball, when we drop the ball, it's going to hit the ground, and then that is going to be a force it's going to exert on the ground, right? It's going to push against the ground. Now, what is the other force? Packer, what is the force that makes the ball come back up? What pushes the ball back up?
It's
What object is pushing on the ball when it's hitting the ground? What object is touching the ball at that point?
The ground.
The ground, right? So the ball hits the ground and the ground hits the ball, right? It's really a lot simpler than we think it is. And that's why Packer's example was a perfect example, because there's another one going on in Packer's example. Before we even drop the ball, there's a force on the ball. Before we drop the ball, what forces are on the ball?
right.
What else?
Our lifting.
Yes, so the ball is being pulled on by gravity. It wants to be pulled to the ground, but the thing that's stopping it is our hand, which is holding the ball. So we're holding the ball and we're doing what? Which direction is the force that we're exerting on the ball when we're holding the ball? Which direction? You're holding the ball, Cole. It's what? Sorry?
Before you drop it.
Before you drop the ball wants to go down. What do you have to do to prevent it from doing that?
Hold it.
You have to hold it in what direction is the force that you hold it with?
Upward.
Upward, right? You have to hold it upward. So you're holding it up, and you really feel this if you've held a bowling ball or a medicine ball. You really feel that you have to hold the ball upward. If it's a smaller ball like a volleyball or a basketball, maybe you take it for granted. But with a heavy ball, you really feel it because it's pulling you downward and you're trying to pull it upward. So you have to hold the ball up, and what's pulling the ball down? Gravity, right? Now here's another one. There's another example in this problem, okay? The Earth itself is actually being pulled on. Did you know that? The Earth is being pulled on by the ball. The ball has some mass to it, so it's like a little planet, a very, very itty-bitty planet. And it's attracting the Earth upward. Right? If the ball that you had in your hands was the size of the Earth or the size of the sun, it would really pull on the Earth. But it's not. It's a tiny little ball. It has a little bit of mass and not much at all. But it does pull a tiny little bit up on the Earth. What prevents the Earth from jumping up and hitting the ball? What is between the Earth and the ball that's holding the Earth down?
The ground, gravity.
Not the ground, not gravity. It's actually something connected to you at the bottom of you. Say it, your feet. You're actually holding the Earth away from that ball. It's like Herculean, your effort, right? That really gives you an idea of how much the ball really pulls on the Earth. It doesn't pull much. You don't have to do much to keep the Earth from moving up towards the ball, right? Because the ball just doesn't pull very hard on the Earth. And the Earth doesn't pull very hard on the ball either. But the ball has so little mass that it actually accelerates towards the Earth. The Earth does not accelerate very much towards the ball. And even if it did, there's somebody in Australia who's also holding a ball and accelerating the Earth in the other direction, so it all cancels out, so you're good to go. If everybody on the Earth all came to North Platte and we all held balls in North Platte, we might be able to, affect the rotation of the Earth or the orbit of the Earth around the sun or something, but we don't. So that was a great example of that ball on the Earth. Can anybody think of another example of a force action-reaction pair? That's what we call it in physics and engineering. We call it a force action-reaction pair, where you have one force that acts on something, and then that something acts back on the thing that acted on it. Can you think of any other examples in our everyday lives? My favorite one is the semi-truck and the fly. Right? So you have a semi-truck driving along the highway, 80 miles an hour, whatever, and you have a fly moving along across the highway as well. And they meet, right? They meet, and the fly exerts a force on the truck. Right?
Yeah.
Does the truck exert a force on the fly?
Yes.
Which one is more noticeable?
The truck exerting force on the fly.
Which one is bigger? What does Newton's third law say?
They're equal.
The first body experiences a force that is equal in magnitude and opposite in direction. So actually, the strengths of the two forces are equal. The force feels the same exact, or the fly feels the same exact amount of force, just in the opposite direction, as the truck feels. So why is the fly's force so much more noticeable?
Because it doesn't have enough inertia. And there's nothing.
That's exactly right. We go back to Newton's first law and we say, well, inertia is an issue here because the fly has so little inertia because it has so little mass, it's going to be very easily accelerated, isn't it? According to Newton's second law, if you have a very small mass and a very big force, you're going to have a lot of acceleration. Let's see what that looks like really quick. So here is our truck, right? Big wheels, big windshield on the front, whatever. This is my great truck. Woohoo! So my truck has got all this huge mass to it, lots of inertia, moving forward here. Here's our little fly buzzing along here. And when they meet, the fly feels this force. Let's say that the force is not even all that big, right? It's just a force, F. But the mass is tiny, and if Newton's second law says that force equals mass times acceleration, if my mass is tiny, if I'm going to get this side of the equation to be equal to this side of the equation, my acceleration is going to have to be big. And the acceleration of the fly is so big that its butt gets accelerated right to its head. And that's why it becomes flat. Because you accelerate the one end of the bug towards the end of the bug so fast that you make him flat. Now, for the semi, it has the same amount of force. But what's the size of its mass? Well, it's huge. It's this big M over here. So what's the size of its acceleration? Itty bitty. Right? So the truck doesn't even feel it. The acceleration that the truck experiences is just, it just needs to keep his foot on the gas for a little much more just because he hits 500 flies an hour or whatever. Right? Those 500 flies an hour do slow down the truck. They really do. And that's actually one of the reasons that they've gone away from the flat-fronted trucks to these new trucks that look like this. These trucks that kind of look like racing cars on the front. Because that actually guides the flies over the top. It creates a wind that goes over the top, and the flies will go up over the top, and the dust and the wind and the air and everything else, so that they can actually be more efficient. That's one of the reasons they put those big wings on the back of the truck and underneath the trailer, those big flat panels as well, because that creates more of that effect and less of the pushing of things around. But this is Newton's third law right here, that the force is the same for both forces. The force is the same on both objects, equal and opposite. But since their masses are different, they experience different accelerations and different effects, different overall effect. Another great example of this is the boxer and the tissue paper. So let's do it. Let's do this example. I need a volunteer. Can you see our classroom here?
Yeah.
You can see our classroom? Okay. Who's going to be my volunteer? Patrick, you've got martial arts experience. Now you're going to have to be my volunteer. We're going to stand over here in front of the pole. Can you see us there? Okay, Packer has martial arts experience. He's a true ninja. Your job is to cut this paper in half with a karate chop.
Okay.
Good?
It's not. No,
No good. Why can't you do it?
because it doesn't have any resistance.
Why not? What happened when you tried to chop it?
Well, it went.
I let go of it, right?
Yeah.
When I let go of it, you tried to karate chop this thing and I let go. It couldn't push back. So could you push on it very hard? It couldn't push back. However, if I hold it really tight and I allow it to push back, then you can cut it in half very easily, right? So if something can't push back, you can't push it, because the force that you push something with is exactly equal to the force that it can push you with, right?
Right.
There's that equal and opposite action-reaction pair. That is used all the time in physics and engineering, science in general. The action-reaction pair. It's extremely important, and it was actually really ingenious. Probably the most ingenious thing that Newton discovered as he was observing things and as he was measuring things. That was probably the most sublime thing and the most important thing and the most ingenious thing that he came up with. And it really made a huge difference in a lot of ways. I just put this up here in the way that I wanted it to go up here. Yeah, there we go. Okay. So, great. Newton's third law. Here's another great example of this. I like this example because I'm a swimmer. I was a swimmer in high school anyway, and a few years after high school. But you have a swimmer pushing off of the wall, and their feet are going to push on the wall backwards, but the wall is going to push them forward. And this happens when we're walking along the floor as well. Which way do you push on the floor when you walk? Which way does your foot go as you go forward? Relative to you, your foot goes backwards, right? And it pushes you forward. The floor actually pushes you forward. And you really know this if you've been to an airport with the little moving walkways, right? The moving walkways push you forward. Right? And even if you just stand still, the floor pushes you forward. And that's the same even if the floor is not moving. The floor pushes you forward. Your foot pushes the floor backwards, right? It's exactly why treadmills work the way they do. Another great example of this is, well, I could go on and on and on. Let's not go on and on and on. So let's talk about systems here for a little bit. Here we have an example where we have the professor pushing the cart of science equipment. You have the cart, you have boxes under here, you have a bunch of equipment on top, you have the professor. What is the system of interest? So the system of interest is going to determine what our free body diagram looks like. If we choose the entire thing here, the professor, the cart, the stuff on the cart as our system of interest, this purple outline here, then the free body diagram is going to include these four forces. The force backwards, little f, usually in physics, little f is for friction. So the little f force is the backward force of friction on the front end of the cart, or the front wheel of the cart. And that's pointing backwards. And this point represents everything inside of this purple box. Now you get that horse joke a little bit better, because now you've reduced a professor, a cart, and a bunch of scientific equipment to a single point. But then you also have the weight of all of this stuff, so the weight of this entire system going downward. You have the normal force, which would go upward. The normal force would act upward from the floor on the professor's feet, upward on the floor from the floor on the wheels of the cart. Anything that's touching the floor and is pushing down on the floor would have a normal force pushing up on it. And all of those normal forces are pushing up in this normal force here. And then we have the force from the floor here pushing forward on this entire system. It's technically only pushing forward on the foot of the professor, but since the professor is pushing on the cart, then that is the force that is the external force to this system. This force that the professor pushes on the cart with is not external to this first system, so it's not in this diagram. The force that the cart pushes back on the professor with is not an external force, so it's not in this free body diagram. Free body diagrams only include a point that represents the system and all of the forces that are external to the system acting on the system. So all the outside forces that act on the system. Now you might want to say that the force of the professor's foot backwards on the floor should be there. But is that force acting on the system? What is that force acting on? The floor, the ground. And the ground is not our system, right? She pushes backward on the ground pushes forward on her, she is part of the system, so that force is in the system. And this is very important because it can get very confusing as we start putting forces together. System 2 would be just the cart. If the cart is the only part of the system, then what forces act on this system? Well, still friction acts on the system, that's little f here. We still have the weight of the system, although it's not going to include the weight of the professor, so it's going to be a different weight. They're going to call it W prime for weight prime for the second weight. And it's going to have a different normal force. The normal forces are only going to be acting on the cart. Since her feet aren't in the system, there's going to be no normal force from the ground on her feet, just the ones from the cart. So that's also a primed force that's different. But the force that is going to push this green system forward is going to be the force from the professor's hand. So that's that force right there in this diagram. So choosing your system and correctly identifying which forces are external to your system and acting on your system is very important when you're setting up a problem with forces. In this problem, what do they want us to do? They have the mass of the professor is 65 kilograms. The cart is 12 kilograms. The equipment is 7 kilograms. So we have 3 different masses all in this particular system if we use system 1. That means we would have to add all of those masses together to get the total mass of the system. And they want to know the acceleration produced when the professor exerts a backward force of 150 newtons on the floor. So this backward force is 150 newtons. How much is this force forward on her foot then, if this backwards is 150?
150.
Yes, because of Newton's third law, right? This is the force of her foot on the floor. This is the opposing force, or the the reactionary force of the floor on her foot forward. So it's 150, it's just the opposite direction. It's the only thing that's different about it. And that now we know is 150. All forces opposing the motion, such as friction in the cart's wheels and air resistance, total 24 newtons. That would be our frictional force. The force from the floor on her foot that pushes everything forward, we're going to consider that our positive direction. The force of friction backwards is going to be considered negative direction in the x direction. And then the upward will be positive, the downward will be negative, so the weight will be negative. And they want to know what is the acceleration of the cart, right? Is the normal force and the weight going to do anything for this? Is this thing going to accelerate up and down at all? No. The normal force and the weight are going to be equal and opposite forces. Okay, so they're going to be equal and opposite forces. The weight, they're not equal and opposite because of Newton's third law. Just so you know. They are both, the weight force is the earth pulling on the cart. The normal force is the normal force is the force that is upward from the earth on our feet. So it's actually the normal force that we feel when we feel our own weight. We feel the upward force that hurts our feet if we stand on our feet too long during the day. It's a fair amount of force, actually. So Newton's second law, rearranged to get acceleration, tells us that acceleration is the net force over the mass. And that can be the total mass here so as well. So we may need to add up, we're going to add up our masses. We add up our masses to get 84 kilograms total. And the net force is going to be the positive force of the floor on her feet, the negative force of friction and air resistance. We add those two together, one of them being negative, we get 126 newtons. Now we have 126 newtons over 84 kilograms. We get an acceleration of 1.5 meters per second squared. What if we do another system? What if we do the system of the professor that doesn't include the professor? It's the same equation. It results in the same things, except that instead of the force from the floor, we're going to have the force from the professor pushing the cart. In other words, we're not taking into account anything that causes the professor to move forward, which also means we're not taking into account her mass. So when we add up our forces, we're not going to get, we're not even going to add up forces, we're going to calculate it from Newton's second law. Because from the first one, we actually already calculated the acceleration. The acceleration is 1.5 meters per second squared, and we know the mass of the cart and all the equipment is 19.0 kilograms. So we multiply the mass times the acceleration of the cart together to get 29 newtons of force for the net force, and then we can plug that into the equation for the net force with the frictional force, and we can get the force that the professor has to push with, which turns out to be 53 newtons. And the reason we put an add in there is because we want to know how much force the professor has to push with to overcome all of these forces. So we rearrange the equation, in other words. This equation comes from rearranging this equation. We add the frictional force to both sides, and we get net force plus friction equals force professor. So you end up getting a 53 Newton force that the professor has to push with to keep that cart achieving that 1.5 meters per second per second squared of acceleration. Why is it less? Why does the professor have to push less on the cart than she has to push on the ground? Remember, on the ground she has to push 150 newtons, but on the cart she only had to push 53 newtons. Why? Why does the professor push harder with her feet down here than she does with her hands up here?
She has to move herself as well.
Because she has to move herself with her feet as well as the cart. That 53 newtons she pushes with her hands is part of the 150 down here. The other 100 or so, 97 newtons, is just to move her own weight forward, her own mass forward. Because with her feet, she has to accelerate both herself and anything that she's pushing. And this is one of the main reasons our legs are so much stronger than our arms. Okay, our legs are so much stronger than our arms because they have to always propel both our mass and anything we're carrying, anything we're pushing as well. Right? So they get a lot more workout. And that is the last of what we're going to cover today, I think. What is today? What is the time? Time. Almost 5. So we've been here a little over an hour. Let's see if we can justify going one more. Yeah, let's go one more section, maybe even two, just so we can have more time on Wednesday to answer questions. Do you need to go somewhere, Paul?
No.
Okay, so let's talk about a few more things. First of all, the normal force, which we've already talked about. Anything that is applying a force to something else, any two surfaces that come together or objects that come together and push on each other, they're always going to have this action-reaction pair, and it's always going to be perpendicular to where they touch. So here's the bow wow chow that you put on the table, and the weight of the bag is going to push down on the table, and the force of the table pushing up on the bag is going to be called that normal force. Before you put the bag down, we have the force from the hand holding the bag up, and after you put it down, you have the force from the table holding it up. In both cases, the force of the hand and the force of the table keeps this bag from accelerating. In other words, it keeps it from dropping towards the earth, right? And so these two forces are equal and opposite, and they cancel out, and that's fine. But these are not Newton's third law of forces, okay? If you want to talk about Newton's third law of forces, you have to talk about the fact that the table feels the weight of the table feels the weight of the dog food. There we go. I'm trying to figure out the name of this stuff. I hate saying bow wow chow all the time. It's annoying. But anyway, it feels the weight of this dog food, and it pushes back with a normal force at that point. But the bag actually feels the normal force from the table pushing up on it. So they're different. They're the same forces, but they feel them differently. They feel them or they experience them differently, I guess is what you have to say. The bag pushes down on the table pushes up on the bag, right? And so on and so forth. And what the bag is, in this particular case, the bag is feeling the weight from the earth. The weight force that the bag is feeling is the gravitational force from the earth, but the table actually feels that downward force of weight and pushes back to the normal force. That's the better way to say it. But it can be confusing, so don't get too frustrated if that confuses you from time to time. It will. It just is that way. Let's look at a really interesting problem here with the normal force. Here we have a skier going down a slope now. In which direction is the normal force going to be? The skier is going down this slope. Can you see the normal force? It's right here going upward and to the left. That is 90 degrees to the slope. It's not 90 degrees to the surface of the earth, which is flat down here somewhere, right? But it is 90 degrees to the slope that they're on. And so now the normal force is actually different than the weight. Here is the normal force going up this way, and there is a part of the weight that is going perpendicular to the surface of the slope of snow. That's this perpendicular version of the weight here, or this perpendicular component of the weight. But there's another component of the weight that is doing what? What does this component do for the skier? This is the one we call We call this the parallel component of the weight. What does this little component of this weight vector do for the skier? Which direction does it point? Down and to the... And which way does the skier want to go?
Down and to the left.
So what does this little component of her weight do for her? For him? It makes them ski, right? Without this slope, the skier could never ski. When you're standing on flat ground and your skis are on, you don't go anywhere because gravity's pulling you down and the earth is pushing you up. And those two forces are equal and opposite, they cancel out. But when you're on a slope, the normal force is tilted. So only part of your weight needs to counteract that normal force. The normal force is actually less than it would be than when you're on flat ground, and you still have a little bit of your weight that pulls you down the hill. The steeper this hill gets, the more of your weight will pull you down the hill and the faster you'll go, right? So this is very tricky. When we do this kind of a problem, we set up a new coordinate system. Our normal coordinate system, of course, would be, horizontal would be X and vertical would be Y. But when we have one that's like this, we call our coordinate system that is parallel to the slope, our parallel, we call that our parallel coordinate, and the one that is perpendicular, our perpendicular coordinate. Now on my computer, this doesn't necessarily look very perpendicular. On the screen up on the wall, it does, so that's good. But this one is perpendicular to the slope, and this one is parallel to the slope. So we're using a new set of coordinates, not X and Y, parallel and perpendicular. And we're going to set up all of our vectors in that coordinate system. So in our coordinate system, the vector that goes straight down, which is the weight vector, is going to have two components. One that is perpendicular to the slope, which is this way, and I like to draw a dotted line down this way that shows me my slope still, which is this way, that's right along the friction there. So I have one that is perpendicular component, one that's a parallel component, perpendicular and parallel. And this is one of those circumstances where the sine and the cosine are going to do exactly the opposite of what they've been doing so far in this class. Notice that this angle right here is the 25-degree angle. It's the smaller angle. And the opposite side is going to be this horizontal direction that's parallel to our slope. So it's going to find out the magnitude of the parallel component, which would normally be our x component or the cosine. You're actually going to use the sine. And you can see that they do that down here. To calculate the parallel component of the weight, they use the total weight of the skier times the sine of 25 degrees instead of the cosine. So that ends up being m times g, mass times gravity, which is the weight of anything, the mass times the 9.8 meters per second squared, times the sine of the 25 degrees, and then the perpendicular one, which is this one here, which would normally be our y component on this tilted axis, this tilted coordinate system. This one is actually going to be adjacent to that 25 degrees, so it actually is the cosine. So this one is the perpendicular component, w times the cosine of 25, where the w is the weight again, and the weight of the skier is her mass times the acceleration of gravity, which is 9.8 meters per second squared. Now you can calculate both of those components. One of those components, this one right here, is just going to be the normal component. But the weight is going to be the one that cancels out the normal component, in other words. This one is the one that keeps her on the slope, this longer one. This is the one that pushes her into the slope, pushes her down towards the slope. But this one here is the one that's going to push her down this way to the bottom of the ski. It's going to push her parallel to the slope, so it's going to be to the bottom of the ski run. And that's going to be the fun component. That's the thing that's going to accelerate her. So that W parallel is the weight parallel, or the parallel component of the weight is the weight component that is going to actually accelerate her down the hill. And so the acceleration parallel is going to equal the force net parallel, which is going to be that weight parallel mg sine 25. Divide that by the mass of the skier. Notice that the masses go away so that all skiers get the same acceleration as long as there's no friction. And it just equals the g times the sine of 25 degrees. This is another thing that Newton figured out. In fact, this is the way he figured out, is by rolling things down downhills. So multiply all those together, you get 4.414 meters per second squared of acceleration going down that hill. Now what would happen if we had friction in this problem? If we had a little friction component, a little friction force pointing upward, back up the slope this way, well that is a parallel to our slope force, but it is going the opposite direction of the force that is pulling us down towards the bottom of the ski run. So these two are going to add together in opposite directions. One of them is going to be positive, one of them is going to be negative. So we take the force net being the W parallel minus the friction off, subtract off that friction, they decide the friction is going to be the negative one. And then that's our net force now. So the net force equals W parallel minus F, mg sine 25 degrees minus F, all over the mass, and you'll get a new value for the acceleration, 3.39 meters per second squared, which is less acceleration than before, and you would expect that. Always check to see if you would get an answer you would expect. You would expect to get less acceleration when you have friction than when you don't. And that's exactly what happens here. Here they have a diagram for resolving those components in a tilted axis. When you have a problem that's on a slope where something is sliding up and down a slope or rolling up and down a slope, you definitely want to change your coordinates to a rotated axis or a tilted axis where you have one coordinate that is parallel, one that is perpendicular, instead of your x and y just being horizontal and vertical. In this case, they're parallel to the slope and perpendicular to the slope. And then you would use a new form for figuring out the components of each vector. Okay, last thing of the day, I believe, for today. It's a big one, we do a lot of them. Is tension. So, tension is a force that is transmitted through a flexible material, a flexible object. Flexible meaning it can turn and rotate, and so it can be a chain or a rope or a cable or something like that. So here is an example of, and it can also, but it doesn't, I apologize, it doesn't necessarily have to be flexible. But it is force that is transmitted along the length of an object, and with flexible objects, it can turn corners. With things that are not flexible, it cannot turn corners. It has to go along the length of the object in the direction of that tension force. But tension is always something that stretches something. Okay? Compression is something that makes it shorter. Tension stretches it and makes it longer. So in this particular example, you have two forces that are on the rope. You have the hand that's pulling the rope up, trying to hold the weight up, and you have the weight that tries to pull the rope down, and so you have the tension force. You have tension forces in the rope on either side. If you're going to draw a free body diagram of this mass, you would have the weight of the mass pulling it down. In other words, gravity is pulling the mass downward towards the surface of the earth. And the tension that is in the rope created by your hand and the mass pulling on the rope in opposite directions, the tension that's in that rope is holding the mass up. So, here is a question. You're holding a mass like this, you're holding it still, and it has 10 pounds of tension in it. And then you lift the mass up higher. You accelerate the mass upward, in other words, higher. Do you add tension to the rope, or is there less tension in the rope, or the same amount of tension when you lift it upward and you accelerate it upward? Should we make it a quiz? So here's the situation. We're holding the mass, just like in this picture. We're holding the mass still, just suspending it above the ground. It has a certain amount of tensions. Let's say it has 10 pounds of tension in the rope. And then I accelerate the rope upward and the mass upward. Is there more tension, less tension, or the same amount of tension when I'm accelerating the mass upward with the rope? We have a vote for same.
More
We have a vote for more tension. We have a vote for less. Okay, we're gonna cover all three bases. Somebody's gonna be right. Okay, so here is the free body diagram before we accelerated upward. This is just holding it still. What's going to happen to these forces if this is going to accelerate upward? One of them is going to have to get bigger. Which one is it? If it's going to go up. Remember that acceleration is always in the same direction as the force that causes the acceleration. So if we're going to accelerate it upward, then the upward force is going to have to increase, and the weight doesn't increase. The gravity doesn't care if you pull upward on it harder, it's still going to pull down at the same amount. So this tension is going to get bigger if we accelerate it upward, so the tension in the rope will get bigger. Now, does that happen in real life? When you have a rope or something, can you accelerate it really quickly and break it, or a string? Can you? If you accelerate it, can you break it? And you break it because you put more tension into it, right? That's why you can pull on the toilet paper in the bathroom really hard, really fast, and it breaks, right? But only if there's a big roll of toilet paper. If the toilet paper is kind of small, what happens? Yeah, you get this like 60-foot long piece of toilet paper rolls out onto the floor, and you're like, ah, crap. But that's actually a perfect example of Newton's third law and Newton's second law, and Newton's first law, actually. Newton's first law says that inertia is going to hold that roll still if it has a lot of mass, and you're going to be able to exert a force on it really quick, increase the tension, and break that toilet paper, right? And there's going to be opposing forces and all that are going to cause that breaking toilet paper. But if you have a small mass, it's going to have small inertia, and it's not going to want to stay still. It's going to start rolling. And then it won't break because it's not going to exert that backward force. It's not going to exert that Newton's third law force. It's not going to break. It's not going to increase the tension very much in the toilet paper. And it's just going to make it roll. It's going to make it accelerate. Newton's second law, right? It's a beautiful example. I wish we should have like little rolls of toilet paper on the walls in the physics room so we can all do this experiment. Or we can go on a field trip to the bathroom.
That sounds so exhilarating.
It wouldn't be the first time I've done a field trip to the bathroom. Field trips, you can do sound, you can do really cool sound stuff in the bathrooms too. You can do resonance of sound waves. We did an experiment that way once in the physics bathroom at BYU. Okay, so here's another great example, and this is an experiment I'm going to have you all do. Do you all have an object in front of you that weighs maybe 5 to 10 pounds? You have a laptop, that's a good one. Do you have something in front of you? There's masses. You can use your water bottle, that's fine too. There's some masses in that bucket there. Yeah, if you have something that weighs a few pounds, even your forearm is enough, really. But what I want you to do is I want you to relax your arm, hang it down so that your arm is hanging straight down. Don't put the mass in your hand yet. And I want you to feel in your arm for your flexor tendon, which is right in your elbow, right in the crook of your elbow. It's the tendon that holds your bicep to your forearm. And if you really push in there, don't push too hard because it can be uncomfortable. You can feel that it's fairly tight even when your arm is just relaxed here, right? You find that where your muscle peaks, it's usually on the inside of your elbow, on the body side of your elbow, that little dimple in your elbow, in the crook of your elbow, go just to the inside of that. And you've got this tendon that's connecting your bicep to your forearm right in front of your elbow, right? Now, lift your arm up so that it's 90 degrees to the ground. You can feel that come out. You feel that come out? Feel how tight that is. Just with your forearm, just with the weight of your forearm, you can actually hook your finger around and feel how tight that is. Just with the weight of your forearm, there's like 100 pounds of pressure on that thing, or more. I mean, the tension in that, 100 pounds of tension, rather. And your forearm is not 100 pounds. Your forearm might weigh, I guarantee my forearm weighs the most of anybody in this room. I have fatter arms than anyone, I think. but mine might weigh 20 pounds, maybe 25, maybe. But most people's forearms are less than that. But there's 100 pounds or more of tension in that tendon. Now put something that has some mass in there and feel how tight that gets. It gets so tight. Now, can you imagine that breaking? What's going to happen to that thing under that amount of tension?
It's going to snap up.
Yeah, it's going to shoot up into your arm and your muscle's going to, it's kind of gross, but what happens? But that's what happens, and that's a major thing to do, major thing to fix. Because the tendons in your body holding your muscles, and they have to hold that muscle at the very edge of the muscle. It's like shutting the door from the hinge side, right? It takes a lot of force to shut the door from the hinge side of your door. But that tendon is under so much tension. This is also true of bicycles. They have this great picture of tension in bicycles. You have, and in fact, they've actually shown it incorrectly. In a bicycle, the tension in your bicycle is actually on the bottom of the frame of the bike, and on the top of the frame you have compression. So it's different on both sides. But here's a great example, the tightrope walker, right? How this is very similar to the tendon in your arm, where you stand on a tightrope and your weight is pulling it down, but the tension in the rope has to pull it up. So how does this work? Well, let's look at the picture. Here is the picture. Well, that's not a very good one. I'm going to draw my own. So here's the picture of the tightrope walker. We have this tightrope, and I'm going to really over-exaggerate the tightrope. It does not bend this much, but over-exaggerating it helps us to see what's going on. Here's our tightrope walker in the middle. Wow, he's got a long torso. And you have this weight from the tightrope roper that is going downward, right? This is the weight of the tightrope walker. You have tension on either side. You have this tension force on this side and this tension force on this side. These two tension forces do two things. The first thing that they do is they tighten the rope. And each of these, let's show our coordinate system. We have an upward coordinate, which we're going to call our y coordinate. And we have a x coordinate, which is our horizontal coordinate. Each of these has two components. It has an upward component that's about that big, and a sideways component that's this big. This sideways component is the thing that makes the rope tight. That's the tension, and that's the pulling on the buildings kind of force. If this was hooked into a hook on the side of the building, the hook on the side of this building would be feeling this sideways force more than anything. But this upward component that's on each force, each of these has an upward and a sideways component. These two upward components have to add together to counteract the weight force. Because if they didn't, this person would fall right through the rope. So if we draw a free body diagram, here's our free body, here's our tightrope walker, then there is the weight of the tightrope roper pulling down. There is the two tension forces that if you add them together, put them head to tail, they will be equal and opposite to this one. And cancel it out so that the tightrope walker doesn't fall. But then there's also a sideways force this way and a sideways force this way that are equal and opposite to each other so that they cancel each other out. These two forces, these upward forces, are quite small compared to these sideways forces in reality. My picture is exaggerated with this really, really bent rope. A tightrope bends very, very little down, which means the tension that you have to put in it is extremely high to counteract the weight of a given tightrope walker. So in this particular example, you have exactly what we just showed you. Here's the tension on the left side. that is this really, really long force that puts a lot of tension in that rope because it's just this tiny little angle, 5 degrees. And then you have the upward tension component, and you have the same thing on the right side. These two little upward tension components have to add together to counteract that weight, and then the two tensions left and right just tighten up that rope, pull it away from, or trying to pull it off the walls. And in the end, if you want to know what the, let's see, what do they want to know? This problem. I don't know what they want to know. They say they want to know what the overall tension in the rope is, maybe. Oh yeah, we're calculating the tension in the wire. So there's a 70 kilogram person on the rope. So that 70 kilograms tells us what his weight is. W is equal to the weight. So the W is equal to M times G. And since he's not accelerating in this direction, then that force equals M times G. This force downward has to equal the force upward. The net force has to equal 0, in other words. And that's a really important concept that we're going to introduce to you right now. Newton's second law says that the net force has to equal the mass times the acceleration. So this is Newton's second law. The net force, or the sum of all the forces, you add them all up, has to equal 0. This has a couple of different, has to equal mass times acceleration. This has a couple of different connotations or implications. First of all, it means that if these are vectors, if the acceleration is a vector and the force is a vector, it means we can split it up into an x part and a y part, which means that this equation also can be written like this. The forces in the x direction, if we add all the forces in the x direction, so we'll write it as the sum of all the forces in the x direction, equals the mass of the object being accelerated times the acceleration in the x direction. And also, if the sum of all the forces in the y direction are added together, then that's equal to the mass of the object being accelerated times the acceleration in the y direction. So once we start splitting our forces into x and y components, then we can split the equations into x and y equations and deal with them separately in x and y, which is a great thing because it makes everything easy. Well, much easier. However, the other thing that we need to realize is that if the acceleration is equal to 0, if a sub x equals 0, in other words, if it's not moving, if it's stationary, or if it's moving at a constant velocity in the x direction, if a sub x is equal to 0, let's make that look like an x, then the equation becomes delta f of x, or not delta, sigma f of x, the sum of all the force in the x direction, is equal to mass times 0. It's just equal to 0 in other words. And the same is true in the y direction. If it's not accelerating in the y direction, up and down, or whatever your y direction is, if a sub y equals 0, then the sum of the forces in the y direction is equal to m times 0, which is just 0. And that's exactly what they've done in this example. In this example, the person is not moving up and down and not moving forward or backwards, so they are stationary, which means that their acceleration is 0 in both directions, x and in y. That means the sum of the forces in x has to equal 0, and the sum of the forces in y has to equal 0. And they actually do the math. Here is the sum of the forces in x. The tension of the left-hand rope in x minus the tension of the right-hand rope in x. They're saying that the left-hand rope is going to be the positive, the right-hand rope will be negative. That's fine, whatever. You add those together, you get one minus the other, and you're going to have to set those equal to 0. So when you set them equal to 0, you find out that they're equal in magnitude. They have the same strength of force, which we already assumed. But if you do the same thing in y, So if you do the same thing in y, you get something a little bit different, because now you have the tension from the left-hand rope upward in y. That's this little guy. That's this little guy right here. And then you have tension upward from the right in y. And you have the weight downward, so you have three forces that are added together. The t equals 0, which is right here. 1, 2, 3 forces added together equals 0, which weight is the only negative one. And then we have a little bit more. We have a little bit more work to do, because the weight is known, but these two tensions aren't yet known. So we have to figure out that tension. So we go back to our x. In our x1, we plugged in our x's into the equation where the force is equal to 0. So there's the forces, the two tensions, that has to equal 0. They're equal to each other. So what we're going to do is we're going to use a trigonometry. The trigonometry we're going to use is with this triangle. We have the tension L in x, we have the 5 degrees, and we have the tension L, which is what we want to know. We want to know this purple side of this triangle. So we're going to use the tangent. The tangent of 5 degrees is the opposite side, tension L and y, over the adjacent side, tension L and x. We do that right here. No, sorry, they do cosine here. So they do cosine here, which is the adjacent side, tension L and x, over the hypotenuse. The hypotenuse is tension L. And then they solve it for tension in L. Once they've written this down, they solve it for tension L. Actually, they solve it for tension L of x. And that equals TL cosine 50. And then, to cosine 5. And then they do tension right in x, which is tension right cosine 5. And that's fine. But since they're both the same, TR right and TR left are the same, which we figured out earlier, then we can just replace either of those with a T. That doesn't tell us everything yet. We still need to know something else. So we go down here and we find out that our net force total is going to equal tension Ly plus tension right y. So the y direction minus weight, that's our y. Again, we get down to a y version of this equation for the sine, doing the same kind of stuff, except this is now in the up and down version. And we get this equation for y, which also leaves us with just a t. So we have try, t sine equals t sine 5 degrees. Now we have a cosine and a sine. So we have TL equals t cosine 5, and we have TL equals t sine 5, and we can use we can do a ratio and use the tangent to find the tangent of 5 degrees to find t. And that's what they do. They go through here and they plug in things and they solve for t, and they get it done. The same thing goes in this kind of a problem where they're trying to pull a car out of here by applying a force here, except now you're solving for this force, and then using the tension to pull the car out. Lots of different examples of how this works. Cables on a bridge. You have cables that are pulling in one direction and other directions, and they all have tension in them. Tension is a huge deal in engineering. We use tension all the time, as well as compression. But that is where I'm going to leave it. I've given you enough, I think, to... actually, no, there's one more we have to do. I keep saying we're done, and then we're not done. But we're almost done. We'll get you out of here by 5:30, I promise. This last one just shows us the strategy for solving these problems. And then I'm going to turn you loose to work on the homework until Wednesday, and we'll come back, do a bunch of examples and homework problems as well. So the first thing in the strategy is to draw a free body diagram. You should be able to go from a drawing to a point with just the external forces acting. Here's Tarzan and his loincloth, right? So that's the first thing that you should know how to do. You should also know that Newton's second law has two forms. It has force equals mass times acceleration, and it has force equals 0 when there is no acceleration, right? Those are two forms of Newton's laws. And then you do it like you do any other problem. You draw a sketch. You're going to identify known and unknown quantities. In this case, we're going to add one more thing by drawing a free body diagram. You identify the things you know, you don't know. You're going to identify the system that you're interested in other words, the things that you want to know the forces on. And then you're going to draw a free body diagram with vectors, the external vectors that are affecting the system, drawn away from the object. Then you're going to write down Newton's second law in horizontal and vertical directions. And you're going to resolve all of your vectors into x and y components for those horizontal and vertical directions. Then you add all those forces together and put them in Newton's second law. And then you solve Newton's second law for the forces that you need to know, put them together, and check your answer. So that's kind of how it goes. We've done it a couple of times today. We're going to do it a lot next time. Next time we'll start here in this section and do some examples. And in the next section as well, and the next two sections actually, further applications and extended topics. But we will cover those last two sections, and then we will do anything in the homework that you have questions on. So get started on the homework, and I think that we'll do the homework due on Fridays from now on, or Thursdays or Fridays, just so you have that extra time after Wednesday to finish it up. And that is that. That's where I'm at. Anybody have any questions before we break at this point? Good to go?
If the tension were less.
Okay. This is in the homework, you say?
No, in the quote.
Okay.
Where. Wait.
Yep.
So what? Ask the question.
So what was when you accelerate it upward? Let me do a really quick here, whiteboard really quick. So in the example that we did, where we're pulling the mass upward, we have this mass that's on the rope, right? And when it's sitting still, the force upward and the force downward are the same in magnitude. And that's why it's not accelerating. Because the pulling force up is equal to the one going down, then that means if we added our forces together, this is a positive force, and this one going down is a negative force, we would get force minus W, and that has to equal the mass times the acceleration of the object, and since the acceleration is 0 because it's not moving, that means this has to equal 0, and that means the force is equal to the weight when you solve this equation. If you solve this equation, force minus W equals 0, you add W to both sides, and this is what you get. So the force is equal to the weight in magnitude, right? In magnitude. But if we pull it upward, that means we're actually adding some force upward. That pull upward is some more force. Just the holding it force was this much. That was just the holding it force, which was equal to the weight force. But the force to pull it upward, we'll call it a pull force. We had to add that force onto it. And so it gives us a little more force in the upward direction. So now, instead of F minus W equals 0 equals mass times acceleration, we have F minus W plus this little pull at the end. And that has to equal mass times acceleration. And since this actually did accelerate upward, because we said that it accelerated upward, it has some acceleration, then that acceleration is not equal 0, and you have to solve this different equation now. And in that case, you're going to get this disparity. You're going to get some extra force upward. It's going to require that. It's going to give you a value for that force upward. Does that make sense?
Yeah.
Mm-hmm.
In my head, I'm pulling up.
Yep.
Like,
Yeah, and so that's another example of our understanding kind of misleading us, you know. For example, when you're in an elevator and the elevator goes down, you feel light, right? When it goes up, you feel heavy. But in reality, your mass hasn't changed. What's really going on? Well, as you're going down, the gravity of the Earth is pulling you down like it normally does, but the floor is not there because the floor fell out from underneath you. And then you hit the floor, and then the floor falls out underneath you. In other words, the floor is moving downward at a speed that is an acceleration that's pretty close to the speed that that the elevator is falling with. So your feet aren't running into that floor as much as they normally would. When the elevator is going up, the elevator's the floor of the elevator is accelerating into your feet, which are trying to go down to the earth, right? And so it's like you're accelerating more into the floor, and you feel more acceleration into that floor and more weight. And so there's a lot of things that are difficult to kind of work out in your head, which is why pictures are great. I'll give myself a star. And any other questions? Are we good to go? Okay, I will post this video. We will meet again. Well, sorry, we're not meeting on Wednesday. We're meeting tomorrow again to give you more insight into this homework. Unless you want to do the lab Wednesday. Which day do you want to do the lab? Tuesday or Wednesday? Do you guys care?
No.
Okay. So let's go ahead and how much time do you guys have before tomorrow to work on this?
But
Is anybody going to work a lot on this before tomorrow?
I can get the assignment done before.
I already did quite a bit done. There's a lot of those that are working right now.
But I'm not this thing. Oh,
Well, let's the next lab, I believe, is the force lab that I gave you. I can't remember what it's called. Can you look in the stuff that I sent you and tell me what the force lab is that I sent you? So we're going so not that one. And that one we could do projectile motion. What's the other one? Combining forces. Okay. So let's do the projectile lab tomorrow. So that'll be our next lab. And then that'll give you a little extra time to finish up homework. If you have questions on Wednesday, we can answer them. All right? So tomorrow we'll do projectile lab. Do you want me to connect so that we can talk about how to do the lab tomorrow? Or do you just want to do it on? Okay. So we'll connect tomorrow and we'll talk about the lab prior to doing it, and then you can do it on your own. You'll need a little space because you'll be shooting things around. You might want to do it outside even. I don't know how much space you have, but inside. But you'll be shooting some things around, and tomorrow, I don't know if it's going to be raining where you're at, but it might be raining here, so maybe it won't work out for you. But anyway, we'll do the lab tomorrow, and we'll see you then. You guys have a good day as well. Did you have any questions, Cole?